Welcome. So what I have here is some questions, additional questions on the final value theorem. So the first set of questions is just based on a closed loop transfer function representing a closed loop control system, all subject to a unit step input applied as acting as the reference. So this question, what we need to do is undertake the following tasks. So determine the final value of the system or the closed loop control system, comment on the steady state error of the system, and then sketch the system response and compare it to the reference. You might also want to label the steady state error. So for these four transfer functions, at the end of this, well, once I've done this initial introduction, I'll run through A and also C. So additional questions. So in this part, I've given you a closed loop control system. What you need to do is derive or come up with the closed loop transfer function and also keep KP perhaps variable. And then for each one of the values of KP, so 1, 5, and 12, what we need to undertake is to determine the final value and also the steady state error of this particular system. Also, you can sketch that on a graph. And then the final additional question is similar to the previous one, but with different KP values. So after I've initially run through the previous questions, so A and C, I will also run through this question. So let's start off with question A. So to begin with, by writing out the final value theorem, so the limit of y of t as t approaches infinity is equal to the limit of s, remember that s, y of s, as s approaches 0. So if you recall from the question, the closed loop transfer function is given by this 2 over s plus 4, which is effectively just, if you recall, r y of s over r of s. Therefore, y of s is equal to r of s multiplied by g subscript l of s. If you recall in the question, we're applying a unit step input for the reference, so 1 over s multiplied by 2 over s plus 4, okay, because that's for the closed loop transfer function. So that is equal to 2s plus 4 if we just simplify it. So then if we apply the theorem, so the limit of s is effectively go to 0 of y of s, because what we're trying to do, sorry I should have said, is we're trying to get an expression for y of s. So that's what we need, so y of s, we've got it here. So which is the reference multiplied by the closed loop transfer function, is 2 over s plus 4. So then if we apply the final value theorem, effectively you can just do that, cross all the s's off, you're left with just the two coefficients 2 over 4, which is effectively 1 over 2. So therefore the final value of the system in steady state is equal to 0.5. So if we want to work out the error is, when we're in steady state, it's just 1 minus YSS times by 100, sorry, because we want in percentage, so it's 1, take away 0.5 times 100, so it's 50%. So what does this look like in terms of the system response? So we've got time, and we're applying a unit step input, so amplitude of 1, and the final system response value, the final value of the system is 0.5. And what we've got is a steady state error equaling 50%. So we could put here amplitude. So that there is A. So now let's move on to another one of these. So let's move on to C. So that was for a first order transfer function. Let's move on to C, where we've got a second order. So I'm not going to write down the rule here, but every time you do a question, it's good practice to just write that down. But I'm going to go straight into just writing out the transfer function. So the closed loop transfer function for the control system is 4 over 2s squared plus 2s plus 4. What we first of all need to do is just divide it by 2 to make this leading coefficient here unity, i.e. 1. So So then we're going to divide the numerator and denominator. So 4 the numerator by 2. So we're going to get 2 s squared plus s plus 2. Okay, and that's obviously your closed loop transfer function. And then if we just recall, as we saw previously, so R of s is equal to R of s multiplied by G subscript CLS. So recalling this question, we've got a unit step input again. So 1 over s multiplied by that here. So 2 over s squared plus s plus 2. Okay, and we can just multiply this all out. So s squared plus s plus 2. Rightio. So what we're going to do now is apply the final value theorem. So the limit s, always remember that s there, s approaches 0. And then y of s, because that's what we need to determine for the final value theorem like we did previously, y of s. So we've got y of s here, so it's 2 over s squared plus s plus 2. So apply the limit, effectively these s's here, just cross them all out. And you can see here we get 2 over 2, which is effectively 1. Therefore, the final value of the system when in steady state is equal to 1. So if we're looking at the steady state error, so the steady state error is equal to, as before, 1 minus the final value in steady state, multiplied by 100 to get in percentage, so it's 1, take away 1, 100, which obviously is equal to 0%, because 1 take away 1 is 0. So what does this look like in terms of the final response? So again, we're going to put a unit step input into the system, so a value of 1, just going to put amp there, time along here. And then what we've got in the final value of the system is 1. Okay, so the reference, so this is what we desire, and this here being y, and this being r, match each other. So we've got 0% steady state error. So the control system there is working as expected or as desired, because we're effectively achieving our desired system response. So now if I move on to 1.2, so additional question 1.2. For this question, the starting point, what I need is, I need the block diagram for the closed loop control system or the closed loop transfer function where R of s is the subject. So it's given by this. So that's obviously your reference, y of s, sorry, not R of s. So y of s is the subject, it's equal to R of s, and then multiplied by this equation here that we'll have derived in the previous video. So where you've got your numerator and denominator of g of s. So just recall that g of s is equal to the numerator of s over denominator of s. And in this particular question, n is equal to 2, and the denominator d is equal to s squared plus 5s plus 2. So therefore, if I substitute these values into here, and obviously at the moment we're keeping kp unknown, just keeping it general. So if I substitute that into here, this is what we get. So y of s, and just note that we've got a unit step input again as the reference. So it's going to be kp multiplied by the numerator value, which is 2. So from there, s squared plus 5s plus 2. And apologies, my s's and 5s look similar. Plus kp multiplied by ns, which is 2. So you can all see that. So d of s obviously is the denominator from there, and that's the equation there. So if we apply the final value theorem, so I'm not going to write down the equation for the final value theorem, you can look back at that, but remember, every time you do a calculation, I'd advise that you write it down in full. Okay, it's good practice. So I'm just putting this down here because I'm going to apply the final value theorem to this now. S squared, apologies, be patient, I'll just write this out. Okay, so if I apply the final value theorem, so that and that, count that. And what I've got left is effectively 2 kp. I'm just going to put the 2 first. And then I've got 2 plus 2 kp. Okay, so that's the equation I've got left there. So when I'm keeping kp unknown. So this now is useful because what I can do is investigate the effect on the final value of the system, of what kp has on the final value of the system. So let's begin. So kp initially, let's equal that to 1. So 2 multiplied by, using this equation here, by 1 over 2 plus 2 multiplied by 1. And then I get 2 over 4. So 0.5. Therefore, y of s is equal to 0.5. And then if we just apply the equation, therefore, when we're in steady state, the error, 1 take away 0.5 times 100, which equals 50%. Okay? Then if we do kp is equal to 5. So again, using this equation here, so 2, 5, 2 plus 2, 5, it's going to equal 10 on the top and 12 on the bottom, which is 0.83. Therefore, y of s when we're steady state is equal to 0.83. Therefore, the error when we're in steady state is 1 take away 0.83 times by 100, which is equal to 17%. Okay, then finally let's do kp is equal to 12. So using this formula again, 12 multiplied by 12 over 2 plus 2, 12 is equal to 24 over 26, which is 0.92. Therefore, steady state, the final value of the system in steady state is 0.92. Therefore, the error in steady state is 1 minus 0.92 times 100, as it has been previously, which equals 8%. So what this is now telling us is that the steady state error of the system is decreasing as you increase the proportional control gain, which is what you might expect because you're effectively putting more power into the system. So what does this look like on a graph? Okay, so each time I'm putting a unit step input in. So we've got an amplitude of 1. And the first where we've got kp is 1, 0.5, and obviously 50% steady state error. And then it's probably going to have a bit of overshoot, and you'll know why that is later. The final value is 0.83 with 17% steady state error. And then finally, this here is 0.92, and here we've got 8% steady state error. And that concludes the question. I hope that's been useful.